first of all, I want to thank the organizers. There are three particular people who are involved, so I want to thank you to Anusha, to Quentin, and to Kirill for their hard work. Plus two more people behind the scene, Christian Sich and Andreas Trabesinger, two people who are really the knowledgeable people, and then they are our guardian angels in the situation. So we always they are always helpful for us. But so what I'm going to talk to you about is nonlinear optics, in particular atomic magnetometry, which is a subject that brought me to the ZULF NMR field. And when we first thought about it a couple of years, maybe a decade back, it was a brand new field. And now, thanks to the collaboration of 9 institutions within, as beneficiaries within this ITN project called Zero and Ultra Low Field NMR, this is growing, and I'm extremely grateful to these people to organizing this, because this can bring this new subject to new people who would be interested in this field. And as you have learned already, the talks are being recorded. They will be published at YouTube. We also have a website where you can go and you can check. This is www.zulf.eu. There's also a blog that will start being available pretty soon. So there'll be all sources of new information and research on this thing. And what I would like to do today, it's a little bit what was covered in the lecture yesterday. I would like to talk to you about a particular tool that can be used for measurement of magnetic spins, nuclear spins, and nuclear magnetic resonance at ultra low and truly zero magnetic fields. So this is the field that is growing, that has many interesting applications, but this talk will be concentrated on atomic magnetometers, particularly those that explore atomic vapors as a sensing media. So I'll talk about some principles of how you can measure magnetic fields to give you some ground, and I talk about some crucial parameters about the zero field NMR. Particularly those that the magnetometers ought to have if they want to measure magnetic signals. I'll give you a particular example how you can build such a system in your lab, or maybe even buy it if you are not willing to do so, and maybe I'll talk with some conclusions. So, as we already said, I'll try to stop at some points asking for questions, but if you have your questions, please put them in the chat box, and I'll try to respond to it when time comes. So anyway, zero field NMR. So maybe let's start with a little of background. I think you've already learned some principles why it's interesting, but in general, this is a field of nuclear magnetic resonance that is measured in very unique experimental conditions. These are nuclear magnetic resonance signals that are being investigated at very low or truly zero magnetic fields. This very low in the context of NMR means that it spans somewhere between zero, truly zero, and above Earth magnetic field, as we've heard yesterday from the talk of Michael Tyler. But in this particular range, the situation is completely different than in usual NMR conditions, where we have a very strong field that determines all the interactions within the molecule. Herein, you're operating under the conditions that internal interactions, in particular J coupling, the coupling between two nuclei, are the strongest interaction in the system in many cases. These are completely different conditions. So although the evolution ought to be very different, as we learned yesterday from Michael's and Thomas's talks, and this new conditions also offer some unique opportunities. In particular, magnetic field is close to zero or truly zero, which means that absolute inhomogeneity of the magnetic field is extremely low, so the lines are extremely narrow. So our lines in many situations are as narrow as tens of millihertz measured in a single shot. And another possibility is that we can investigate whole molecule at once. Of course, in nuclear magnetic resonance, you have a specific detector that is tuned to a particular particular type of a nuclei. Here, you can have an access to the whole molecule at once, of course, as long as this contains spin 1/2 nuclei. So this gives you to the access to the whole molecule at once. And while this is interesting thing, we've learned yesterday that there are some reasons why people are working at high field using very strong superconducting magnets. So if you want to operate under different conditions, in particular when you want to measure signals at zero field, you have to address some problems. And we have heard about the problems. One of them is polarization. So you have to find an interesting and maybe smart way of polarizing your sample, preparing your sample before you measure it. And we've heard about remote polarization, when you pre-polarize your sample somewhere outside, and then this sample is transported into a low or zero field region where you can investigate its evolution. Another possibility is using hyperpolarization, when in some situations you don't even need magnetic field whatsoever, so you can do all of the measurements in situ, so you can evolve this. Of course, if you want to do this, you want to keep one of the biggest advantage of NMR. You want to keep its analytical capabilities. So you want to investigate the chemistry of the molecule. And we've learned that at zero field there is no chemical shift, so you cannot explore chemical shift. But on the other hand, what you can do, you can explore this inner molecular interaction. So in particular, J coupling, so the interaction between two nuclei that is mediated by the electron of shared electronic cloud. And the last but not least, what you have to do, you have to somehow address the problem of detecting NMR signals at zero field, because the scheme, the sensor that is typically used in such measurements, the coil, is sensitive at higher frequencies because it measures the changes of the flux. So the faster the flux changes, the higher is the sensitivity. And of course, the flux change is determined by the magnetic field. So you want to replace this by some other sensor. And of course, this other sensor that we'll be talking about is atomic magnetometer. So what is an atomic magnetometer, sometimes called optical magnetometer, sometimes called optically pumped magnetometer? This is actually a device that measures magnetic field by investigation of properties of light that is transmitted through a medium that is subjected to the magnetic field. So in the left corner, you see a simple example of some scheme. You have your pump laser, you have your probe laser, you have your magnetic field, you have your sensing element, you have your atoms, and then of course you have some means of detecting changes of light properties. So by investigating the change of the light intensity or the change of the polarization as a function of the magnetic field, you can extract magnetic field. So these basic ingredients in the picture are, of course, light. So you need to have photons, and atoms being the second ingredient, or more particular, their spins, atomic spins in the situation. When you get these two things interact, and then you have your system that is subject to magnetic field, you can think about detecting magnetic fields in optical manner. So how do you do this? What is the basic fundamental principle of measuring this? Well, when you think about an atom has electrons and the atom has a nuclei. So in many cases that will be considered today, at least during this talk, we are considering situation when electron is in at the electronic shelf, that says the total angular momentum equals to 0. So the total spins of the electron is actually spin 1/2 in the situation. Then the spin 1/2, although coupled with a nuclei, forming a total spin, or total atomic spin in the system. So this atom has a spin that is being seen from the outside of the environment. Now, in a thermal equilibrium situation, you don't know what is the orientation of the spin, or more precisely, this orientation of the total angular momentum is undetermined. Every single direction, every single orientation is equally probable in the system like this. So we don't know what it is, and if you like to use a quantum language, we say we have an atom in a mixed state. So most probabilistic state in the situation. So what we do right now, we are illuminating our atom with a beam of light. Of course, beam of light is a beam of photons that are being, moving with respect to some object, with respect to space. And of course, to keep interaction between these two elements, between atom and spins, you have to conserve some laws. So, for example, to excite the atom, energy conservation rule has to be fulfilled. But also momentum conservation has to be fulfilled, and the most important in this situation, angular momentum, has to be fulfilled, because photons are particles that are having spin, and of course this spin somehow corresponds to the properties of light as a wave. So in particular, what you are seeing in this picture is that these photons that looks like this C-shaped elements, the wave is circularly polarized, what means that its projection onto the quantization axis is along the light propagation direction. So now when atom absorbs light, it is being excited, but although angular momentum, projection of angular momentum is transferred to atoms. So now you break the symmetry between all the orientations, and now your direction is being perfectly determined, or at least on average it's determined. What is interesting in this picture is that when you do it for a long time and you pump all the atoms, because all the atoms in the system, and atoms has a finite angular momentum, you can end up in a state that being fully polarized. So we have a full polarization of the system, which is very interesting because it means that the system that was initially resonant to light, that was absorbed to light, becomes transparent to light, because these atoms cannot take any more angular momentum to itself. So now the light can be transmitted through the system without being absorbed, even though the light is resonant with a specific transition. So now we should say the following thing. So you polarize the spin, and of course, with the spin or angular momentum of the atom, and with this angular momentum, there is a magnetic moment associated. So now, if you take this system and place it in a magnetic field, it will start to precess. It will precess around the magnetic field, which means that now the precession, which is perfectly determined by the magnetic field, modifies, for example, in this picture, transmission of light. Because when the light was along this projection of spin, there was no absorption. But when it's rotated by 180 degrees, it's exactly anti-parallel. So the probability of absorbing photon is very high. So what you're seeing is, you see this modulation in absorption of light in this scheme, and this modulation is determined by the magnetic field, because this is nothing else but the Larmor frequency. The Larmor frequency that is determined by the magnetic field and a gyromagnetic ratio of your system. So now you can, by observing light modulation, you can actually tell what the magnetic field is. But truly, the real problem is that in the system that we are which are actually very dilute gases, there is 10 to the 9th to 10 to the 14th atoms in a cubic centimeter, which means that the dynamics of such system is much more difficult. There are complex processes that are arising in the system. So when you're pumping the system, you are generating some dynamic equilibrium between different processes, and you are generating some sort of either dynamic equilibrium or some static equilibrium in the system.
Shimon,
yes.
we have a question. So James asked, when the atomic medium becomes transparent to light, does that depend on whether the light is linearly / circularly polarized?
So that it can depend, it can be transparent in either situation. It can be transparent for linearly polarized light. It can be transparent for circularly polarized light. So there are different scenarios in which this can happen. But there are some assumptions that are really swept under the rug in the situation. But yes, the answer is it can be either in a linear situation when you pump in with linearly polarized light. It could be circularly polarized light of either right hand or left hand helicity. Okay, so let me maybe go one more slide, and maybe we can stop to have some more questions. So what I want to say right now is that the sensitivity of magnetic field detection in the scheme really depends on your ability to determine, or precision of determining the spin orientation. And how well you can determine your spin, this actually depends, it actually determines what is the situation. So before we jump there, before we ask ourselves, so how precisely we can determine the magnetic field, we should talk about two different situations in which you can study the dynamics of the system. So first situation is that when you don't have a single atom, you have many atoms, and you pump these atoms with circularly polarized light. If you do this, you have no control over timing of the interaction. So when each atom absorbed light. So they can absorb light in a different situation. They can respond differently to the magnetic field. So they actually, instead of seeing this oscillation in the system, you are generating some equilibrium, dynamic equilibrium situation, which is a compromise between precession, between optical pumping, between relaxation in the system. This means that you can, with such a situation, you can have a magnetometer that measures magnetic field very sensitively, and it is realized in a relatively simple apparatus, because you don't have to modulate light, for example, in the system, but it has some drawbacks. These two particular drawbacks I would like to mention here is that this curve, which is a dispersive curve that we are seeing on our plot, needs to be calibrated, because what we are doing, we are, for example, measuring this optical signal. It could be, for example, polarization rotation, a linear polarization rotation while traversing the medium, and we need to calibrate this polarization rotation so we know what magnetic field it corresponds to. This is a difficult situation because this curve, the width of the curve, the amplitude of the curve, depends on many parameters, such as like light intensity, the temperature of your sample, the composition of your sample. So you have to do it carefully, and you have to some control over your experimental parameters.
May I interrupt you again? We have one more question. So again from James, he asks, fully oriented includes fully aligned. So is oriented transparent to both? Or when you say aligned is transparent to linear light, does that mean the specific case of zero net orientation of the atoms?
Okay, so if I think the answer is the follows. If I can generate a transparency with a given polarization, I can generate transparency for this particular polarization. So if I'm using circularly polarized light, this medium may become transparent for circularly polarized light. But at the same time, when I would send a linearly polarized light through this system, with this fully polarized system, I would have an enhanced absorption of one polarization component over the other one. So I can actually have some strong polarization, or even step further, if I pump the system with right-handed circularly polarized light, when I send a left-handed circularly polarized light, this medium will be absorbing even more light than before. So the transparency actually happens for this, well, most often. Of course, the situation is more difficult, but in a simplest scenario, the transparency happens for the polarization that we are using. So if you polarize with circular, you get a circular transparency, and so on and so forth.
Okay, thanks, Prima.
Sure. Okay. So to finish this cons on the unmodulated light magnetometers, one important disadvantage is this sensitivity range for the magnetic field detection. So the dynamic range of the measurements is actually limited to a very weak magnetic field. So typically on the order maybe of something like 100 nanotesla or something like, sorry, not 100, 1 nanotesla or something like this, something very, very narrow. So to address this issue, you can replace your CW light with a modulated light. So now you are not strobing, you're not illuminating your atoms with a CW light, but you are strobing, you're flashing light on your system. This means that you have some sort of a control over the time that when it's interacted. So even if you are not controlling exact timing, by appropriately choosing the timing of this or the frequency of this modulation, you can synchronize precession of all spins. So now all spins will be moving synchronously, and what happens a little bit. This reminds us a little bit of a situation of thermal equilibrium. Do you see me? Because I disappeared for a second.
Yes, your network was poor, I think, for a while.
Okay, sorry about this.
Now it's fine.
Okay, so now what you can do, you can have a sort of you can have somehow a little bit of a pendulum, because the amplitude of these oscillations is actually depending resonantly on the precession frequency. So if your modulation frequency hits the precession frequency, you have the highest amplitude in your system. So you can observe the system. And now when magnetic field changes, now they go away, so the amplitude drops. So now you can adjust the precession frequency, the modulation frequency. So now once again you are seeing your signal. So what it means that now you are prolonging your dynamic range. You can track magnetic field in much broader range of magnetic fields, so particularly all the way to the Earth magnetic field. So you can expand the dynamic range by maybe 4 or 5 orders of magnitude in the situation. But this also comes with some caveats, with some problems. One of them is that now you need to modulate your light, so your system, your experimental system, is a little bit more difficult. The other thing is that typically this offers slightly lower sensitivity, so you have to agree that you are not having the full sensitivity of the system, but on the other hand, your dynamic range is much broader. And I think this is a good point where we can stop, and I would like to ask you if you're having some other questions.
I don't see any questions in the chat box, but I can wait a couple of seconds. Okay, we don't have any questions right now. Maybe you can continue.
Okay.
Okay, thanks.
So now the question is, what would be the sensitivity of the of such measurements? Well, if you think about sensitivity, you can instantly think about two scenarios. One is a fundamental limit on the sensitivity. So what is the basic level, the lowest sensitivity you can achieve? And then the other one is what is the real sensitivity that you will achieve because of this environmental thing, because different interactions, different something that happens to your system. So let's start focusing on the first part first. So what are the fundamental limits? We've already said that two main our optical magnetometer is light and is our spins, atomic spins. So light and atomic spins and spins in general are quantum elements. So in particular, light can possess something that is called a photon shot noise, which means that number of particles in a light beam, number of photons in the light beam of a given intensity is fluctuating. So if you measure the number of particles in a one time slot and in the other time slot, you will find that there is a small difference between them. And this is not a difference that is related with that your laser is not good enough, that you are not controlling some of your elements in the system. It's a fundamental fluctuations that is related with a quantum nature of photons. So you cannot really estimate, based on this, you cannot really estimate the intensity of your lights because it fluctuates a little bit in your system. The other thing is that these fluctuations can also act on your spins. So now there is a small fluctuation of light intensity on your spins, which means that now your spins are also observing or having this extra noise in the system. And this extra noise, so there's some additional uncertainty in the spin polarization. And now this uncertainty in the spin polarization comes back to your spins and then affects a transmission of light. So this is something that we call the back action. So because of the interaction of light with atoms and then atoms with light, these fundamental fluctuations of photon flux of a number of photons also manifest itself as an ingredient, as a source of noise in our system. And the last but not least is that we are talking about spins, and spins is a quantum property, so it is quantized in particular. So we cannot exactly say that what is the orientation of the spin. So there is some uncertainty stemming, for example, from Heisenberg uncertainty principle that we cannot say. This is what we call the spin projection noise. So this is our inability, fundamental inability to determine the orientation of spin in our samples. And these three things are the fundamental sources of noise in our system. But what you can do, you can play with them a little bit. You can limit, for example, the photon shot noise, make it much, much smaller. You can somehow try to limit the back action, and then what you end up is this spin projection noise. The main source, the most fundamental in per se, source of fluctuations in our system. So this brings us to the equation, to the only equation, well, maybe not the only one, but one of a very few equations that we are showing, but the most important equation in our story, the equation that was called by our next speaker, Dima Butker equation 1. So this is an equation that determines the atomic.
Shimon, may I interrupt you? So Michael Taylor say, I don't fully understand the principle of back action. Can we have some more explanation?
Sure. We can understand it in the following way. So if you want to be rigorous now, so you have your light and you are sending light through your photons, and of course, at the detection stage, for example, you don't want to perturb your light very strongly. So what you are doing, you are using off-resonance light. I believe Michael is using off-resonance light at his probing stage. And of course, this off-resonance light is not being strongly absorbed. It's not being strongly perturbing the spins. But there is some sort of an interaction because we are still observing the rotation of the polarization plane. So there is some sort of an interaction between the atoms and spins. And this particular interaction that we are observing is what we call the dynamic Stark effect. So this is a change of spin precession or the distance between the magnetic levels that is caused by off-resonance light. This off-resonance light pulls the levels closer to one another, for example, and modifies the precession frequency in our system. So if it does, and this precession frequency and this how close they are depends on the tuning, but most important on the intensity of light. So if you are fluctuating, if your intensity is fluctuating, then your levels are moving back and forth, and this brings some uncertainty. This brings some noise to our system. So now the spins are being a little bit smeared out in our system, and because of that, now when these smeared out spins are affecting propagation of light through your system, you are taking this uncertainty and you are bringing it back to photons. So this is like a loop. This is why it's called a back action. Light affects atoms, and atoms affect back light, and this is how this uncertainty is propagating in the system. I'm not sure if this is enough or this is clear enough for Michael. Shall we proceed?
Sure, he said yes.
Okay. So now let's go back to our equation 1. So this equation 1 depends on several things. The first thing is what stands in the front of our right-hand side of the equation. So something before the square root. This is actually a material parameter. There are things that are. This is a parameter that is determined by what sort of an atom we are using. Either we are using rubidium or a different isotope of rubidium or cesium. We have a slightly different number. So this is mostly a gyromagnetic ratio that we are having here that is being determined. But of course, the sensitivity of the measurement also depends on different factors. So for example, if you keep measuring, if you keep repeating, or if you keep measuring for a longer time, precision of your measurement should increase. Well, of course, this is true when there are no systematic slow drifts, for example, of your signals. But if there are no fundamental limitations, the longer you're measuring, the higher is your sensitivity of higher is the precision of your measurement. But not always you can increase the length of your measurement. Sometimes you have some limitations. So there are two last most important parameters that affect the sensitivity of magnetic field measurement: the number of atoms that you are using and the transverse relaxation time that that your atoms possess. So namely, how long does it take for spins to dephase in a given magnetic field? These two parameters are the main parameters that we are fighting with in building optical atomic magnetometers. So before we talk about these parameters, let me do a little bit of a detour in here. Because to understand properly the role of these two parameters, we should mention that the magnetometers that explore vapor cells for their alkali metal vapors for their operation, so something that we are discussing here, are using rubidium, cesium, or potassium sometimes. Why these elements? Why? This is the reason for that is that all these elements are alkali atoms, which means that have only one single electron on the valence shelf. So this is a system that we can somehow describe, and this is well understood. The single valence electron provides us with a relatively simple electronic structure, so the energy level structure is simple. We can also manipulate with these electrons, and in general, the total atomic spins, angular momentum, by applying light, appropriately polarized magnetic field, either oscillating or static, or by applying different electric fields and so on and so forth. So we can actually explore this system. One more important parameter is that all these alkali atoms are having very strong transition, the lowest energy transition in the system, which we call D1 line, is actually very strong, so that even 10 to the 9th atoms in a couple of centimeter long cell can absorb a significant fraction of our light. And this light can be generated, once again, very important thing, can be generated with the lasers that are very simple, because all these lasers are diode lasers. So for example, you can buy those lasers for a very little money and use it for the thing. And last two important elements of the system are the following. If you are using alkali metal vapor, this is vapor, so you can control the vapor by changing the temperature. So for example, in the plot on the right, you'll see that when you increase the temperature of rubidium vapor, you can change the concentration of our system, concentration of our atom, by a few orders of magnitude. So for example, coming from 50 to 200, we can change the concentration from maybe something 10 to the 10th to something to 10 to the 14th atom. So we have a control of the concentration. And last thing is that since these are alkali metal vapor, and these are rather dilute media, you can assume something very important. You can assume that all the atoms are being independent from one another. Hold on, let me finish. Are independent from one another, and then you can measure. We can treat them. We can apply the same mathematical procedure to describe them. Yes, please.
Sorry. So you mentioned the strong absorption. Is it related to the probe or pump beam?
Well, the strong absorption is of course related to the wavelength of your light. So if your pump is tuned to resonance, you are talking about strong absorption. Typically, you want your pump being strongly absorbed. Then, of course, you have your probe, and as we mentioned before, you don't want strong absorption of your probe, so you want to detune it, and then this absorption deteriorates with the frequency. So you can actually have a very weak absorption of the probe. But in a scheme I will give you in a second, we have only a single beam, so this will be also a little bit different. So anyway, the most important, the strong absorption is when you have your light tuned to appropriate wavelength.
Okay, now Kirill wants to ask you one question. Can I ask him to unmute his?
Absolutely, please.
Okay, Kirill, please.
Thank you. Szymon, I have two simple questions on basic things. First of all, so what limits the frequency range in unmodulated case of the magnetometer?
You mean the bandwidth of the magnetometer?
Yes, right. Okay.
I will talk about it. I will talk about it in 3 slides.
Okay, great. And then question about the previous slide. About the equation number 1. So if we acquire for infinite, I'm a little bit confused. How this equation applies for different schemes? For instance, in case of modulated, unmodulated. I guess there are a lot of stuff dependence on frequency and so on.
No, I don't. Well, I honestly don't think that it depends on the frequency. I think you're confused that if you are measuring for a longer time, that the precision is higher and higher, or the sensitivity is lower and lower.
Yeah, that's so okay. I'm confused in several ways. So first of all, if the T2 is too short, then I don't understand how just by acquiring more noise we can get some additional.
No, but you have to assume that we are measuring. You can think of this as a repeating of a measurement.
Okay, I see.
This is not one measurement and your signal decays and it's done. You are constantly pumping of the system, right? So you're renewing your situation. So you can think about it as a repeating of a measurement over and over and over again. So if you replace this time by a number of measurements, it will be true too, right? So So this is not that you are observing a decay time and then you are observing 0. No, this is you are repeating, and repeating. You keep your resonance, you keep your oscillating signal all the time.
Yeah, I see. Yeah, thank you. And last is that again, it seems that there are different ways to detect different, like non-modulated case, modulated case, but still the equation 1 is same for any of them. Okay, I see.
Yeah, because we are not talking about detecting anything. We are talking about our ability, or maybe we are talking about a limit on our ability on detecting a specific spin projection. So you don't know. This is universal in a sense.
So this is just dispersion of magnetic field, right? This BAT. I guess this is this is.
No, so this is what this number, what this BAT means is that this is the smallest magnetic field that can be detected. This is the fundamental limit on the smallest magnetic field that stems from the atomic projection noise.
I see. Yeah, I see. Thank you.
Okay, thank you, Kirill, and thank you, Szymon.
I'm not sure, Dima, because it looks like I'm running out of time and I'm not even close.
I think you have 15 more minutes.
Okay, good. So let me now come back to equation number 1, because this was brought by Kirill in here. So we have these 2 parameters: the number of atoms and the transverse coherent relaxation or transverse polarization relaxation time. So if we are talking about alkali atoms at room temperature, these are dilute gases. We talk about 10 to the 9th atom per cubic centimeters. This means that the mean free path between 2 collisions of atoms is on the orders of hundreds of meters. So these are very dilute media. So if you contain this media in some bulb, we call it a glass cell. If you contain it in a glass cell, then this is much more probable that it will collide with walls than with one another. So what you want to do, you want to prevent the collisions with the walls, because the collisions with the walls destroy your coherence, destroy your polarization. So you do 2 tricks. One trick is that you put some layer inside the walls, and then this layer prevents from depolarizing within the collisions. So this is something we call paraffin or anti-relaxation coating that we put on the walls. The other thing is that we introduce into the cell some buffer gas, typically a noble gas or molecular nitrogen, that has a high pressure. And what is unique in this situation is that the collisions with these atoms do not destroy coherence. So now, since there's a lot of buffer gas atoms, they do not freely move in the system, and rather your alkali atoms are diffusing towards the walls. So it takes time, it's much longer, so you can significantly prolong your lifetime. So you can beat a little bit of the time T2. But then you can do the second thing that we talked about. You can try to increase the concentration. And you start increasing the concentration, which means you are heating up your system. And the number of atoms is increasing, but suddenly at some temperatures of maybe 50, maybe 80 degrees C, the concentrations becomes significant. So now we are talking about 10 to the 12 atoms in a cubic centimeters, and they start to collide with one another. And this turns on some important relaxation mechanisms. One of them is called a spin exchange relaxation mechanism, in which 2 colliding atoms are reversing their spins, which is actually a bad thing because they start to precess in opposite direction. So the effect of this collision, they start to precess in opposite direction and they start to lose their coherence. So the spin exchange collisions are actually destroying our polarization. So at some range, we are actually not increasing sensitivity because we are increasing the concentration, but at the same time, because of the collisions, we are decreasing T2. We are decreasing transverse relaxation time, which I'm sorry, yeah, we are decreasing this. So there's a stable situation. You are not winning anything. But what becomes very important, and this was a discovery more than 15 years ago, or it was demonstrated more than 15 years ago and applied, was something that was noted by Will Happer 3 decades ago, probably, that when these collisions become very often, so they are colliding very fast, the spin relaxation mechanism is being switched off. So they are trying to rotate in one direction, but they are colliding, so they are rotating in the opposite direction, and they are going back and forth. And you would think, okay, this is zero. But since there's a little bit more weight into rotation in a specific direction, they effectively rotate in a given direction. So what is happening? Now you switch off the magnetic field, you reduce T2, and you have a lot of atoms. So now you can you have relative sensitivity, and somewhere above 200, maybe between 150 and 200 degrees C, this effect, another relaxation mechanism are kicking in, and they start to once again deteriorate our T2. So this is why in our talks that we have yesterday, we talk about specific temperatures at which we are operating our sensors. The temperatures were somewhere between 150 and 200 degrees C. This is explored in what we called spin exchange relaxation free, or ZULF magnetometers. These are the magnetometers that are extremely sensitive. So on the top of this fundamental noise, there's also experimental noise. Your system is in real environment. So for example, you use light, you illuminate your system with laser light that fluctuates a little bit because there is some electronic noise that appears in your signal. And for example, you are seeing all these 50 hertz and harmonic signals in your system. Then you have motion of air that affects the system. You have vibrations, you have electronic, and so on and so forth. So you have many effects that actually affect your sensitivity. So your fundamental sensitivity is at some level, but typically the real sensitivity that you're observing in a system is significantly larger in this area. So to give you an example, I listed a couple of magnetometers, the optical atomic magnetometers that are being used. And second to the right column is actually fundamental sensitivity limit. And then the last column is the demonstrated sensitivity limits in our magnetometer. So as you see, these are actually, these are typically an order or maybe even 2 orders of magnitude worse in different scenarios. But one important and one positive information is that the sensitivity of the system is on the order of some maybe tenths of femtotesla, because we have the system that are extremely sensitive, and you can achieve the sensitivity of 10 to minus 15 Tesla per root hertz in our system.
We have a question. Light shall interact with gas only, or this could also work with liquids and solids?
This is a very good question, and I think you are the good person to respond to this question. And I also would like to say that the next speaker will be talking about it. But in general, the problem is that in solids and in liquids, your T2 is extremely short. So your electronic transverse relaxation time is extremely short, which means that you are that while you're having a number of atoms, a lot of atoms in your system, at the same time you're suffering from very weak, very short T2. So in principle, you can do it. And then, of course, there are optical magnetometers based on, so for example, some crystals. But these are typically many orders of magnitude worse in sensitivity than what we are discussing here, except some specific examples we will hear later today.
Okay. Also, I would like to remind you we have only 5 more minutes left.
Yeah. So let me jump to 2 more parameters. So bandwidth is actually another parameter that you're being interested, because you have your magnetometer, and this magnetometer may be very sensitive but very slow. But in NMR, you want to detect signals that oscillate at some specific frequencies, be able to detect this frequency. And in typically bandwidth of the magnetometer, of optical magnetometer, is being somewhere between 1 hertz and maybe 100, maybe several hundred hertz. And as was asked by Kirill, what is it, this bandwidth being limited by? Actually, the same parameters that determines our sensitivity also determines the bandwidth. So this is T2. But in contrast to sensitivity, where the larger T2 corresponded to better sensitivity, here the larger T2, meaning the narrower bandwidth. So always somewhere you have a compromise between these 2 parameters, between sensitivity and a dynamic range that you are observing. So you have to choose. Luckily, in optical magnetometers, you have some knobs that you can play, that you can, for example, adjust this T2, and then, for example, sacrifice a little bit of the sensitivity, as we see on the plot in the right bottom corner, but then get a much better bandwidth. So we can, the closest to us in the plot is the very narrow bandwidth, but we increase the bandwidth with increasing light power, and we can reconstruct the whole pulse that we are observing in our system. And finally, another parameter that is important is a type of the field that you want to detect, because sometimes you want to detect a static field, and sometimes you want to detect oscillating magnetic field. And luckily, there are magnetometers that are offering either detection of a static field or a detection of the oscillating field. So you can have your magnetometer that measures magnetic field, or you can have your magnetometer working as radio, where you tune the frequency of this radio so that you are exclusively sensitive to a specific frequency. And this will allow you to detect a specific frequency band, which is a narrow band filter, and you can filter out the signal of interest from your situation. So this is interesting in a situation when you want to detect some signal at higher frequencies. So since I'm running out of time, let me just tell you a few things if you want to build a system like this, because these principles are relatively simple. And actually, if you want to build a system like this, if you want to build a magnetometer, you can do this. What you need is a laser that emits a linearly polarized light, and you can transform this light into a circularly polarized light, as we see here. And this circularly polarized light is being sent through the vapor cell, which contains rubidium or some other alkali gas, which contains a buffer gas. So, for example, nitrogen or helium. And it's being heated to some 150, 180 degrees C. At this temperature, we are operating in a surf regime. And what we are doing is very simple. We are looking at the intensity of transmitted light. So if you scan the magnetic field, you will see something like this. You are observing the resonance in your system. But now what you can do, you apply the magnetic field in a particular direction, perpendicular to the light propagation direction, and this modulation is very broad. So the amplitude of this modulation is actually much broader than the dynamic range of the magnetometer. So you would expect it to be peaking once in a while when you're going back and forth. But you are doing it very fast, which means that you are doing it much faster than the bandwidth of the magnetometer. So you're not observing this peak, but you're actually observing something that reminds you of harmonic oscillations, maybe harmonic oscillation with a second harmonic, as we are seeing in this plot. So now you are demodulating the signal at the modulation frequency, and you observe a very nice, very low noise signal that you can use for magnetic field measurement. So you reduce your noise, you can increase the sensitivity, and this is actually a plot from our magnetometer that operates exactly at this principle that shows you the sensitivity of something like between 40 and maybe 50 femtotesla per root hertz, and at the same time has a bandwidth with a cutoff frequency at maybe 450 hertz. So something that is extremely important, extremely interesting in the context of zero field measurement, zero field NMR. But you might be lazy, you might be not a physicist, you don't want to do this. So what you can do these days, you can actually go to the shop and buy such a magnetometer. So there are at least 2 companies I know about that you can go and buy a system. So now you're having a sensor that has a very good performance that can be placed, it's turned on, and it gives you the result. So you can, if you want to measure this, you can, zero field NMR, or you want to measure magnetic fields, you can buy a sensor like this. But if you want to measure if you want to measure zero field NMR, if you want to measure ZULF NMR, for example, you need some extra elements. So you need, for example, a magnetic shield that isolates you from uncontrollable magnetic fields. So you can buy this shield. So once again, from TwinLeaf, they are doing something extremely nice. You buy such a shield, and now you can put your magnetometer inside, and you are more or less ready to detect. Because these shields are also having magnetic field coils, and you can supply the coils, you can generate magnetic field, you can generate magnetic pulses, you can buy the sources of this, or as we've heard about from the talk by Michael Tyler yesterday, you can buy a pulsar, and you can actually have this nearly ready to build component to build a setup. So you have many commercial components that you can buy, and if you're a chemist, you don't have to hold the apparatus on your own. You can actually put it from component. But if you wait for a little bit longer, you may be able to buy such a system commercially. Because if you are a chemist, you should look into TwinLeaf website, because we are collaborating with them to build a setup, a very small setup that will be able to detect zero field NMR. So what you are seeing on this picture is actually a ZULF NMR spectrometer that can cost something like 10K, probably in some foreseeable future.
Szymon, I'm afraid we are already crossed the time.
Okay, I'm having 2 more slides. Just maybe I want to say one thing. So now you have your apparatus, you have your system, you can measure your system, but of course zero field, you have to be careful, because this atomic magnetometry should remind you nuclear magnetic resonance, because more or less they work on the very same principle. They observe the spin precession. But at atomic magnetometers, the spin precession is governed by the gyromagnetic ratio that is some hundreds of times larger than in nuclear case. So you can what you can actually do, you have to be careful. If you apply the magnetic field, you have this magnetometer that is having completely different sensitivity range than the frequency emitted from your atoms. So you have to be very careful, and you can play with the tricks mentioned by Michael Tyler yesterday. You can have a solenoid that generates a different field for your sensor and different field for your NMR sample. You can measure something very close to magnetic field or truly in zero magnetic field, and you can do some other tricks like flux transformer that I'm not mentioning. So with this, I want to say a couple of things. I want to say that atomic magnetometers can be used to detect nuclear spins, and there is a vast field, vast application. We'll hear about more of them in the future, in the next talks over the next couple of days. These magnetometers are becoming portable these days. So, for example, this is a magnetometer that was built by Piotr Put in Berkeley this spring. It was transportable, so you can call it portable ZULF NMR magnetometer. So this is becoming more like a real tool where you can take it to the chemistry lab. And then there is a whole range of commercial possibilities if you want to get into this field, but you are afraid of all the physics and all the kitchen related with building such a setup. Pretty soon you'll be probably able to do it yourself. And with this, with showing my collaborators, the most important people in my group and my main collaborators, I would like to finish and thank you for your attention.
Thank you, Szymon. That was a wonderful talk, wonderful lecture. Maybe the floor is open for question. We already have one question from Arun. He was asking, could you comment on noise in case of light interacting? In case of light interacting with the liquid / solid, like contribution of back action, etc. In solid bar liquid samples compared to gas phase, will spin projection be still the dominant source of noise in liquid bar solid? And he also remarked, nice talk.
Thank you. So the answer is yes, it will be the dominant. While we can increase the light intensity, and in a sense, we can reduce the noise of photon shot noise. When you can reduce, when you can limit your back action by the tuning or properly tuning your laser, you will be not able to significantly reduce T2, which comes from some local environment, from local magnetic fields, local electric fields that are arising in this scheme. So if you want to have a correspondence, you can think about EPR, electron paramagnetic resonance. This is exactly the situation. The times that you're having in electron paramagnetic resonance are actually the times that we are talking about in a case of liquids and solids in the situation in optical magnetometers.
We have one question. Does zero field mean no static magnetic field?
It does. Zero field means no static magnetic field whatsoever. So it means that we are, well, of course, this is a little bit broader in a sense. We've heard about it. It doesn't mean that when we have a zero field, we have no magnetization in our system. We do have a magnetization in our system. This magnetization evolves due to some J couplings and other interactions, but the truth is that either we have no magnetic field whatsoever, or we have a very, very, very weak magnetic field that, for example, now, as was shown by Michael yesterday, can split our J coupling lines into two lines, and then we can explore some different scenario. But in general, yes, no static magnetic field whatsoever.
Okay, we have one more question. If one wants to determine bulk polarization of hyperpolarized one-net signal, which setup can be the most effective and cost effective? And he also has some connected question. Which light source should be used? Which field should be used? Can we use earth field?
Sorry. So the first, let me check if I understand correctly. So the question is how to determine the polarization using hyperpolarization?
No, he is okay. If one wants to determine bulk polarization of hyperpolarized one-net signal, which setup can be most effective? I'm sorry.
I think I would say a conventional NMR would be the most effective in the system if you wanna measure this. But of course you can also bring a sensor and you can measure magnetization of the system. But to be completely honest, I would say a conventional NMR system might be the best solution for measuring the degree of polarization of the system.